In this video, we're going to be talking about conics, so I'm going to first start off by defining what a conic is. It is an intersection of a plane and a double-napped cone. The four basic types of conics are parabolas, circles, ellipses, and hyperbolas. In these conics, the plane does not pass through the vertex of the cone. So as you can see in the figures below, that the intersection of the cone would be in this place, but whenever a plane does pass through this vertex, they're called degenerate cones, which look like this. If the plane passes through only the vertex, a point is formed. If the straight line is formed if the plane is tangent to the cone's surface. So we just have a straight line going through here. And a pair of straight lines is formed when the plane passes through the vertex and intersects the top and bottom halves of the cone. So it's just a straight plane down the middle. Okay, the first thing we're going to talk about is parabolas, and the definition of a parabola is the set of all points equidistant from a line and a fixed point on the line. The line is called the directrix, and the point is the focus. Now the point on the parabola halfway between the focus and the directrix is the vertex, which is your HK, and the line containing the focus and the vertex is going to be called your axis. Now this parabola has an axis that is vertical. Now if you look below, this is the standard equation for a parabola with a vertical axis of symmetry. So to find the vertex, you all know just to look at the equation and pull out the x and k that it gives you. And then the focus, because it's going to be on the same axis as the vertex, it's going to share the x-coordinate in common. To find the y-coordinate, you have to add p, which is this distance here, to your y-coordinate of the vertex. Now to find p, you set whatever coefficient is on the outside of the parentheses here equal to 4p. So let's say you have 16 on the outside of the parentheses, you put 16 equals 4p and solve for p, so you would find that p equals 4. So then you would take that 4 and add it to the y-coordinate of the vertex to get the y-coordinate of the focus. Now the directrix is a line and not a point, but it's very simple. All you have to do is take the y-coordinate of the vertex and subtract p, and that would give you the line here. Below we have a parabola that has a horizontal axis of symmetry, and as we all know, this equation here is not actually a function, but for the purpose of conics, we will be talking about this type of graph. Finding the vertex is the same, you just have to be careful because what's inside the parentheses has switched just because we're changing the direction of the graph. So now your h is going to be on this side and your k is going to be on this side. So the vertex is still going to be HK. Now the focus, instead of adding p to your k, you're adding p to the x-coordinate because of course we're going left or right, not up and down now. So we still find p in the same way. You set your coefficient here equal to 4p and solve for p. And the directrix, instead of it being set equal to y, it's going to be set equal to x because of course it's now going to go up and down rather than side to side. So instead of subtracting p from k, we're going to subtract p from h. Okay, next we're going to be talking about the reflective property of a parabola. So we're going to let this point here be point P, and this straight line here is going to be the tangent line to our point P. So the reflective property is basically saying the line that passes through the focus and the point P, and then the line passing through P, that is parallel to the axis of the parabola are going to make equal angles with the tangent line. In this example, we're going to be finding the vertex, the focus, the axis, and the directrix of the equation. Now, this equation is a representation of a parabola, so the first step is to change it to the standard form. What we're going to do first is isolate the y, so we're going to add 8y to both sides. Next, we need to group our x's in order to complete the square. Now, to complete the square, you take half of b and square it. So we're going to get a positive 4. And what you do on the inside, you must do the opposite on the outside. So we're going to have to subtract 4 from the 28. Now you have a perfect square, so it's going to be x minus 2 quantity squared. So next, after we have subtracted 24 from both sides, you can easily factor out an 8. And it's going to be 8 times y minus 3. Now your equation is in standard form, and the vertex is going to be 2, 3. If you just look at the equation, it's going to be hk, so that's an easy one. The next thing we're going to find is the focus, which is h, and then your y-coordinate is going to be k plus p. So what we need to do is set 8 equal to 4p and solve for p, and we get that p is 2. So now all we have to do is add 2 to our k coordinate, which is 3, so we're going to get 2 and 5. The next one is the axis, which is an easy one because all of our x coordinates are going to lie on the line x equals 2. The equation for a directrix is y equals k minus p. So all we need to do is 3 minus 2, and you get y equals 1. Now we're going to be talking about ellipses, and the definition of an ellipse is a set of points such that the sum of the two distances from any point on the ellipse to two other fixed points is constant. The two fixed points are called the foci of the ellipse. So basically what this definition is saying that this line, the distance of this line and the second line to this point from the two foci are always going to equal the same distance, no matter if the point is here, here, or here. This is an example of an ellipse with a horizontal major axis, which is the line segment containing the foci and both endpoints of the ellipse, which are the vertices, and it also contains the center of the ellipse. Now, below it here is the standard equation of an ellipse with a horizontal major axis. So to find the center, you find your h and k in the equation, which is like parabolas. To find the vertices of the ellipse, you're going to have to find a, which you just take the square root of whatever a is here, and you add that to your x coordinate because, of course, since our major axis is horizontal, we're going to be moving left and right, so we're going to be dealing with our x values. And then you use the same y coordinate as your center, and to find the foci, you're going to use your equation a squared plus a squared minus b squared equals c squared to find your c value, because of course you have a and b already. So once you find that c value, you're going to add and subtract it to your x coordinate and use the same y coordinate as your center to find your 2 points where the foci are located. Now you see in this ellipse we have a vertical major axis, so our standard form is going to change a little bit. The only thing that's different is our a and b has switched. To find the center, still the same thing. Our h and k are going to be in the same place, obviously, because even if you switch this around to where it has a horizontal major axis, the center is always going to be in the same place. Now to find our vertices, it's going to be a little different. All we're going to have to do is add that a value to our y coordinates instead, because we're going to be moving up and down now. And same thing for the foci, we add that c to our y value. Next, we're going to be talking about the reflective property of an ellipse. The property says that let P be a point on the ellipse, which we have labeled right here, and the tangent line, which is a straight line here, to the ellipse at point P makes equal angles with the lines through P and the foci. So if you look at the two line segments from the foci that meet at P are both going to have the same angle measure with the tangent line. Now we're going to be talking about the eccentricity of an ellipse, which is simply represented by E equals C over A. Now looking at our ellipse here, we know that C is the distance from the center to one of the foci, and A is the distance from the center to one of our vertices. Now, from looking at this ellipse here, we know that A is always going to be greater than C, so we can assume that eccentricity is always going to be less than 1 for our ellipses. Now, up here we have a few examples of eccentricity measurements. So as you can see, the closer we get to 1, the more oval our ellipse are going to get. In this example, we're going to be finding the major axis, the center, the vertices, the foci, and eccentricity of an ellipse. The first step to make it into standard form is to add 6 to both sides. Next, we're going to divide both sides by 6, so our 2 is going to cancel out, leaving 3 at the bottom, and the 3 is going to cancel out, leaving a 2 at the bottom. And you're going to get 1. So now our equation is in standard form, and the major axis is going to be horizontal because A is always going to be the larger denominator, and A is under the x squared, not the y squared. So if you just go back and look at the standard form equations, you'll see why it is horizontal. The center is going to be 0, 0, because nothing is being added to the x squared or y squared, so it's going to be hk. The vertices are going to be 0 square root of 3 and 0 negative square root of 3, because the equation for vertices is hk plus or minus a. And in order to find a, you have to take the square root of 3. Next, we're going to find the foci. In order to find the foci, it's h, and then your y coordinate is going to be k plus or minus c. So the equation to find c is c equals the square root of a squared minus b squared. So now that we've found a squared and b squared, all we have to do is plug it into the formula. So now we're just going to simply get 3 minus 2, which is 1. And remember, since you're taking the square root, it's plus or minus. So now the coordinates for our foci are going to be 0, 1, and 0, negative 1. Next is finding the eccentricity, which is basically how narrow or how big our ellipse is going to be. The equation for that is c over a, so we simply plug in the numbers and we end up with square root of 3 over 3. Last but not least, we're going to be talking about hyperbolas. The definition of a hyperbola is a set of all points such that the difference of the distances between any point on the hyperbola, which I've labeled P, and two fixed points is constant. So our fixed points are always going to be the two foci on either side. So what this definition is saying, that say there is a line going from point P to this foci and a line going from P to this foci, the difference between the two lines is always going to be constant no matter where this point P is located, even if it's located here, here, or here. Now, the line segment containing both of the foci is called the transverse axis, which is here, and the endpoints are the vertices which are at the very tip of the hyperbolas, and then that the center is exactly halfway between the two foci. Now, if you look below, this is our standard equation for a hyperbola that has a horizontal transverse axis. So to find the center, we always do h and k. To find the vertices of this hyperbola, you would find the value of a, which is you just do radical a, and add that to our x coordinate, because of course, since it's horizontal, we're looking at left to right. And then we would use the same y coordinate. And the same thing goes for the foci, except we're going to use the value of c, which again can be found by using our equation c equals radical a squared minus b squared. Now we have our hyperbola with the vertical transverse axis. So below here is the standard equation for this type of hyperbola. The only thing that's really changed is where the a and b are located. Now the b squared is under the x and a squared is under y. So the center always hk. The vertices are going to be the same concept, just you're adding the a now to the y coordinate, and the same goes for the foci, you're adding the c value to the y coordinate, because of course now we have the vertical transverse axis, which means we're going to be dealing with our y's going up and down. The next simple thing about hyperbolas is the asymptotes. So these two equations are used to find them, because of course you're going to have two asymptotes here. The only difference between the two is this one's adding and subtracting. All you would need to know to plug in numbers into these equations is the center, hk, and the values of a and b, which again can be found from the standard form of the equations. And after you plug those in and simplify, you will get your equation for the asymptotes. Now for eccentricity of a hyperbola, it's found the same way as an ellipse, c over a. The only difference is c is the distance, of course, between the center and the foci, and then a is the distance between the center and the vertex. So this ratio is always going to be greater than 1, because c will always be greater than a. So as you can see here, the closer the eccentricity is to 1, the more narrow our hyperbola is going to be. And when the eccentricity is large, it's going to open up our hyperbolas a lot more, as you can see here. In this example, we're going to be finding the standard form for the hyperbola and finding out if it has a horizontal or vertical transverse. Our first step is to subtract 2 from both sides and start grouping our x terms and y terms together. I factored out a 5 from our x terms and factored out a -3 from the y terms. And now to complete the square, it's going to be a +4 and a +1. And what you do to one side, you must do to the other. But don't forget, we have a constant on the outside of the parentheses. So we're gonna end up adding 20 and subtracting 3. So now we have perfect squares, and don't forget your constants on the outside of the parentheses, and the other side is going to equal 15 after we simplify. So now you divide both sides by 15, and then you're going to end up with your standard form for the hyperbola. And because we're subtracting the y terms, if you go back to your standard forms for the equations, we're going to see that this equation has a horizontal transverse. That concludes our conic video. Hopefully it doesn't completely suck and I get a decent grade.